So as you already know, we did a little bit of work with an ammeter, so you already know ammeter, am, sounds like amp, ammeters measure current. The idea is to figure out what the current passing through a given circuit element is. In our case, the current through a particular resistor. If we want to measure current, that means we should set up the ammeter. How should we set it up relative to the resistor we're trying to measure the current through? Well, we know that when circuit elements are in series, that the current passing through them is the same because of conservation of charge. So if you want the ammeter to measure current, it should be set up in series with whatever it is you're trying to measure the current through. Now, whenever you take a measurement in any system, you don't want the measurement to affect what is actually happening with the system. If you do something that changes the system, if your measurement changes the system, then you aren't getting a legitimate measurement of what was going on before you inserted your measuring device. So if the ammeter is set up in series, well, if it had resistance, then that would change what's going on with the circuit. It would change the amount of current flowing. So an ideal ammeter has a resistance of 0, because then you can set it up in series, and it won't affect the current flowing through the circuit element that you're measuring, that you're trying to measure the current through. In reality, of course, even wires have resistance, so ammeters never have 0 resistance, but in practice they work effectively if the resistance of the ammeter is low compared with the other circuit elements. Or also it can work just fine if the resistance of the ammeter is known. If you know what the resistance is, then you can account for that when you're dealing with your circuit. In a circuit diagram, an ammeter is just represented with an A, a circle, and then you draw wires coming out from either side, attaching to whatever else it's attached to. A voltmeter, as one might expect, measures voltage, or remember the technical term for voltage is potential difference. And I'll just write also known as voltage. Now, if you want to know potential difference, well, you're trying to find the potential difference between two different points. Usually those would be points on either side of a circuit element, the voltage drop across a resistor, for example, or the voltage of a battery, or whatever. So you need to attach it to points that are on opposite sides of the circuit element, and that means that it is set up in parallel with what you are trying to measure. Now, if we're setting up another parallel branch, again, you don't say for a resistor, for example, if you set up a wire parallel to a resistor, all the current's going to go through the wire now, and there won't be any current passing through the resistor, so you'll change the voltage drop across the resistor. The same is true if you set up so you don't want to provide an alternate path for current to flow. So in order to avoid changing the voltage drop across the resistor, the ideal voltmeter has infinite resistance so that it is not providing a new path for current to flow down. It is not shorting out the resistor at all. And a voltmeter, just like an ammeter, you just put a V in a circle, and then the wire is connecting to wherever it's connecting to. This isn't going to be relevant for our purposes in this lab, but it's possible that it could show up on the AP exam. A multimeter is a device that can measure multiple things, often both current and voltage, potentially other things as well. But just so you know, if I'm at AP exam, you're asked a lab question that includes something something to do with a multimeter. I know what a multimeter is. So just thinking about this, let's say the circuit diagram here. Just to think about what's going on. Draw where you would insert an ammeter to measure the current passing through R2. Well, current passing through R2, to figure that out, we need the ammeter to be in series with R2. So where would that go? Well, we would cancel out, separate our wire here and instead connect our ammeter so the current will pass through the ammeter and then into the resistor. Or you could do the same thing down here. So imagine this wire, whatever attachment is going on here is deleted, and then an ammeter is inserted instead. Voltmeter needs to be in parallel, so you want the voltmeter to connect to the 2 points you're measuring the potential difference between, which in this case would be the 2 points on the opposite sides of the battery. So put a voltmeter right here, and now we'll measure the potential across the battery. Now suppose the ammeter has an internal resistance of 0.25 ohms. Calculate the percent difference in the current passing through R2 as a result of the ammeter. Now this is more complicated. We're going to have to use Kirchhoff's rules to do all this stuff. Well, let's get to it. Actually, or not. This is the same circuit, I believe, that we did on the previous day, wasn't it? Yeah, this is the same circuit we did back here in number 22. So at that point, our equations were this: negative I1 plus I2 plus I3 equals 0, 305 I1 plus 100 I2 equals 15, and then negative 100 I2 plus 395 I3 equals 25, and we got these values. I1 equals 0.052, I2 equals negative 0.0089 amps, and I3 equals 0.061 amps. Okay, now we want to figure out how R2 is changed by the ammeter if the ammeter has an internal resistance of 0.25. Well, what does this do? This means that there's a resistance in the ammeter that's in series with the resistance of R2. So essentially, R2 is being increased by 0.25. So what are our equations then? With the ammeter, what changes? Well, not a whole lot. Our junction rule still holds. We've still got 305 I1, but now instead of having a resistance of 100, it's as though the resistance now is 100.25. Now, if you stop and think about this for a moment, you will realize, you can think about it, resistance of 0.25 versus 100, versus 100 ohms, that's not a large percent difference. So I'm betting that this isn't going to have a drastic effect on the current passing through I2, but we can go ahead and run the calculation. And actually, I still have the matrix in my calculator. So I can just go ahead and change the 100 to 100.25, change this negative 100 to negative 100.25, and then run RREF, and now what do we get? We get values for the other two, but I2 is equal to negative 0.008916863, whereas before it was negative 0.00892 something. So we can see there's not a whole lot of difference. 2 minus 0.008916863 divided by 0.00892, okay, times 100. So we've got about a 0.035% difference. So again, you see that practically speaking, as long as the ammeter's resistance is much smaller than the resistors in the circuit, it doesn't cause a big change in the values of your currents.